Great. All right, so I'll use these 10 minutes just to talk a little bit about a problem where in resilience, actually, resilience for multi-robot systems, a problem that I've been thinking about for some time, and we've been doing quite a bit of work in this area. And the question is, how can we use the physicality of these multi-robot systems to actually make them more resilient? And so to really motivate this idea, first, I'll just pose a few examples of how we're thinking of multi-robot systems going into the world around us and being able to perform tasks that are important for society, kind of at that interface of society, like smart and connected vehicles, using robots for environmental monitoring, autonomous delivery, rideshare, search and rescue, smart manufacturing. When you start thinking about these problems and you think about how robots can start to become part of the fabric of society, the questions of security for these systems and resilience of the algorithms that are dictating their behavior becomes really important and really obvious that this is something we have to think about. So in the example of, for example, smart and connected vehicles, an adversary or a hacker that gains access to this system can alter the behavior or the coordination. But these algorithms are known to be vulnerable. So for example, there are classical results that show that if some larger proportion of the network is compromised, say by hacked agents, this can actually be very detrimental. And so these algorithms are vulnerable. And this is not just something in theory. This is something that has been looked at, is on the radar of governments. It was named as one of the grand challenges for the National Academy of Engineers. And there are technical reports about how cyber-physical systems, for example, are vulnerable. And so the question is, what can we do on the research front? And so just to be a little specific, what I'm talking about for resilience is the following: the degree to which success of some coordinated objective, say platooning on a highway for a group of autonomous vehicles, the degree to which that coordination can be achieved is what I'm going to call performance. And then the degree to which that performance can be attained even in the face of adversarial attacks on the network, I'm going to call that resilience. And so the idea here is that we have to be able to characterize and mitigate the impact of untrustworthy agents or information in the system. And so that's a lot of what we do. And so to make this a little bit more concrete, looking at the example of consensus, this is the case where you have autonomous vehicles that are platooning down a highway. Some other vehicles need to merge onto the highway, and part of that decision process is consensus. And so here, vehicles might need to agree on their heading, they might need to agree on their common velocity, and this would be the ideal case where on the right-hand side, you have a plot of agents agreeing, say, on their true average velocity. Now, the problem with this is that if there's heterogeneity in performance that can be caused by, for example, adversaries, this can create problems for the team to be able to actually agree and could create difficulties like collisions or the platooning group splitting apart. So here you have an example of what this looks like in an actual multi-robot system. So here you have legitimate robots, most of them, and you have one malicious or adversarial robot. And these robots are essentially trying to agree on a particular direction, heading direction, as in the example that I showed. And here, as they're moving, they're running a consensus, and that's what you see here. On the lower left-hand side. And then at some point when the communication network is vulnerable, because this malicious agent is creating a bottleneck in the structure, what you see is that if the malicious agent decides to attack precisely at that time, it can actually create a confusion in the system, which can have adversarial effects, where agents cannot agree. And this, because consensus is core to a lot of coordination algorithms, this kind of generalizes beyond consensus. And so in general, there are different approaches to security. Some of them are graph or structure-based, where the idea is that no matter where the malicious agents are in the network, so long as they're limited in their number, the algorithms can still be made robust against them. And so this video shows kind of an example of the previous video that I showed, where now, and this is some work that we did to show that that consensus can be made resilient so long as certain connectivity infrastructures or certain connectivity structure is maintained throughout the route. And so here, the consensus is indeed successful, and this was something that we published in RSS, and then TRO as well. Okay, so that's one approach, but the approach that I want to talk about here is more on the physicality side. So how can physicality help us here? And the fact that robots are actually sensing their environment. They're not just networked entities that don't have actuation and sensing capabilities. And I want to use that in particular to help us get past one limitation with the graph structure-based approach, which is that the number of malicious agents that can be tolerated and is pretty restrictive. So if you have more than half of the network connectivity being malicious, that's very difficult to deal with. At the same time, it's very difficult in practical settings to actually guarantee that you won't be hitting that limit. So what can we do? This is the next part of the work that I want to highlight a little bit and kind of put some ideas out there, food for thought. So the idea here is that these robots can actually sense their environment. They can sense each other. They can use that information in their algorithms. And so in particular, they have onboard sensing, they have onboard compute, they have distributed sensing by communicating with each other. So the key idea is, can we use that additional information that we get from this physicality to measure a form of interagent trust? And if you can quantify this, then you can link this with the control and make it much more resilient. And that's kind of the key idea of this part of the work that I want to highlight. And so there's been a lot of work that shows how sensing can be used to understand the trustworthiness of a system. And so I want to highlight some of that. But then at a high level, what we're really looking for is this concept of quantitative trust. And this is an idea that we're developing, but that's really essential to be able to use this concept of trust in the control, in a closed loop. And so that's the ultimate objective here. And so the idea is, if we had some additional information that could be quantified, like some alpha value, that captures the likelihood that any agent I'm communicating with is trustworthy, then this could allow us to break past these classical results in resilience that make the practicality of multi-agent systems limited in real-world settings. And so we've taken that idea and we've done quite a bit of research in resilient distributed consensus, resilient distributed optimization, and hypothesis testing. I won't go into this, but I will just highlight what this looks like. So I'll take this distributed hypothesis testing example and put it up here, kind of as food for thought also. So here, this is inspired by crowdsourced mapping, like say Waze or something like this, where agents are essentially communicating with some central server or some cloud server, and they're giving observations of whether a road network that they're on is crowded or not, congested. So we can put like a traffic map. Now, if there are adversaries in this system, say some of these agents are actually hacked, the idea is that those hacked agents are trying to flip the bit at the cloud server. And so this is what this looks like in an actual experiment. So here we have a mock-up road network where you have robots, and some of these robots are actually adversarial and they're spoofing other fake entities into the system. So this is a Sybil attack. And the idea is that the fake entities can communicate to the server that a road network is congested when it's not, or is not congested when it is, to confuse the server or flip the bit at the server. But we're using the physicality here by also sensing over wireless signals and using those wireless signals as a fingerprint. So if you do that, the Sybil entities don't look unique, and that's what this is showing here. And so that's this alpha value, and we're able to show in experiments that indeed we get a nice stochastic, of course, because this is noisy. These are real systems, but you get you get the ability to start to classify which agents you can trust and which you cannot. And so what that looks like in this setting here is that if you look at agents that are traversing over this road network, here's the ground truth of whether these segments are actually congested or not including the Sybil entities, which are kind of shown a little bit faded, the Sybil entities. And then this is the oblivious fusion center that takes the Sybil inputs as actual. And then here's the average percent error. And so we're able to show that we can get a much better understanding of the true congestion, even under a Sybil attack, when we are using this additional information that we get from the sensing over the wireless channels. And so I'll just quickly summarize here that we are looking for a general framework for quantifying trust. Wireless signals are one example that we've been able to explore and show that does work in this context. But really, the important characteristic is that we need some way to quantify a difference between malicious agents or hacked agents and legitimate ones. And then that can be very powerful for the controllers. And in particular, it provides a bridge between theory and practice. And so I'll stop there. I'll mention that some other work that we've done is in using robots to rendezvous with whales at sea. And the major problem there is sequential decision making that's adaptive to real-time sensed information, which is also important for the embodied theme. So I won't play this video. I'll just leave it there, but I'm happy to talk more afterwards. Oh yeah, and of course, acknowledgements. I would like to make sure to acknowledge the students and collaborators and funders that make the work possible. Thanks so much.
Great, thank you, Stephanie. So questions for any speaker, please type it in, and also themes for the panel. So I think we're supposed to run for another 25 minutes discussing, anything from the talks or possibly also anything else. I don't know, maybe I was wondering the connection between like Heroku swarms and your multi-robot things. Can you guys touch on that?
Yeah, I was fascinated to see those robots moving around. So, yeah. So, do you plan, Stephanie, do you plan to scale up the system you are proposing to not only just a handful of robots, but maybe hundreds of thousands if they are actually deployed in the real city of Boston, for example?
Yeah, that's really interesting. So we've been mostly thinking on like tens of robots type scale, but the ideas and the concepts here are generalizable because they're distributed. And so we can think of scaling them up. We haven't tried doing that because we do need some computation on board. But fundamentally, I don't see a limit there. And in fact, thinking kind of broader scale in terms of swarm and maybe even miniaturizing this, there are some interesting questions on the immune systems and immune system cells and things. So I think that could be a nice bridge, because there you're very much trying to understand which cells are trustworthy, if there's a virus potentially in the system that needs to be detected and attacked. So I think there are very interesting ideas there. We don't have that expertise in our lab, so we haven't quite looked in that domain, but I'd be very interested in thinking about what this concept of quantifiable trust might look like at those kind of smaller scales, and perhaps more swarm type of systems. Hiroki, for some reason I couldn't hear.
What I said is because you are at Harvard, you may want to work with the people working on kilobots. You know the kilobots?
Yes, yes.
Yeah. I think we got some questions right on chat. Mate.
Yeah, well, there is one. I'm not sure I understand it, but I'm going to read it out. Is there any consideration for robots that fail naturally, as in due to environmental dangers?
Yeah.
Yeah. Do you want to take that, Hiroki?
Yeah, sure. Go ahead. Yeah.
Okay. Yeah, so in our work, we have thought definitely about failures because some failed robots can also look untrustworthy. So it is possible that that happens. I guess what we've been looking at are more like explicit attacks. So when an agent is very intentionally trying to attack the system, because there you have a large amount of bias that comes into the system and it can be very detrimental to coordination. But you can imagine that there's some work. And in fact, there was one of the papers that I mentioned here by Alyssa Pearson had a very interesting take on heterogeneous performance and being able to adjust like an adaptive coverage controller based on that. So their failed agents would have a lower performance score. And so you can imagine definitely of thinking about that under the same umbrella of quantifying trust in a sense. But we're really looking for something a little bit more general that can handle like very strong biases that could come in because of intentional attacks. But thanks for the question.
Okay.